Hi, yes, I'm Ariel. I'm currently almost wrapping up my PhD at the Polytechnic. In the meantime, I've started working at a small company called Air, where we do human-in-the-loop learning. But in this work, we simulate virtual humans. So it stays kind of in the same area. The general setting that we worked with in this paper is crowd simulation using deep reinforcement learning. So we want to simulate little virtual humans, little agents, which in practice are sliding cylinders because they don't focus that much on the body animation part. And we want them to move around in a shared space to reach some goals that they have set, ideally to avoid collisions, and also ideally to move in a human-like manner. But then the problem is, okay, what does it mean to move in a human-like manner? How can we define it? How can we quantify it? So in the reinforcement learning framework, we tackle it by designing an appropriate reward function. So in reinforcement learning, just to give some background to anyone who might not be familiar, the general idea is that we give the agent, we specify a reward function which is defined for every action that the agent takes, and then we just let the agent learn somewhat from trial and error. The agent tries to do something, it receives a positive or a negative signal that will tell them, okay, this is a good action, this is a bad action, and then they just try to adapt their policy to, on average, get a higher reward rather than lower. So what movement can we actually count as a human-like, even if we're just humans looking at it and trying to give an answer? That's pretty difficult. But then how do we actually quantify it? How can we convert a trajectory or even a single movement into a number that says, okay, on a scale from 0 to 10, how human-like is this? That's also not the easiest thing. Then there's also a few things that we need to consider on the pure kind of reinforcement learning engineering, let's say. Just like, how should we design this reward? Should it be dense or sparse? There's some implications to that. Should it maybe be positive or negative? There are sometimes some implications to that. And finally, does it actually matter? Can we just design something that makes some intuitive sense and then just optimize it and then call it a day? Well, this has been done many times before, and the results are, it kind of works, but it does not look very human-like. So what we propose to do, instead of designing something arbitrary and just hoping it works, is using the idea of energy optimization. And this is an idea that appears in many places in natural sciences, in other crowd simulation work, and just kind of everywhere in the world, that the trajectories that humans or beings or cells take are the trajectories which minimize the energy usage or perhaps the perceived effort for humans. And in this work, we estimate the energy by using this formula, which is taken from some biomechanical research, where, as far as I understand, they put a person on a treadmill, they tell them to walk at a certain velocity, and then they measure the CO2 in their breath to estimate how much energy they use. And this seems to generally work, but there are two questions. Is it actually general? Because the scope of the research that I mentioned, so you put someone on a treadmill and they walk at a steady pace. They do not accelerate, then they do not turn. So this equation does not give us the full picture. It gives us an approximation for steady movement in a straight line. And then can we just use this as can we just take this, maybe we do something with the acceleration and can just optimize this as a reward function and then call it a day? And of course the answer is also no, it's never that simple. So to tackle the first problem, the generality or the acceleration problem, is like we propose an extra term, which here in this in a relatively simple case of accelerating, it boils down to adding an extra term proportional to the acceleration and to the velocity, which turns out, if you do the math, this corresponds to the increase in the kinetic energy that your body gains as you accelerate. There's a bunch more nuance if you consider deceleration, if you consider turning, so there's some vectors and vector math involved. The details are, of course, in the paper. But to give a basic intuition on how this impacts the energy usage, I admit this is sometimes a slightly difficult to understand graph, but the premise is that in the current time step, we move at the velocity of 1.3 meters per second. This is where the orange and the blue lines intersect on the right side. And then in the next time step, we'll move at some velocity, which is shown on the x-axis. And then in that process, we will use the energy, which is shown on the y-axis. And the idea here is that if we add the acceleration correction, if we want to accelerate, we will use much more energy than we would have otherwise estimated. If we want to slow down a little bit, just kind of by not putting in any effort into moving forward anymore, we actually use a bit less energy. But if we want to stop really abruptly, then we have to use energy into the stopping process as well. And then the second problem, the optimization. So let's say we take the original energy equation, or we take the kind of adjusted, the corrected energy equation. So can we just take that as the reward function and optimize it? And no. And there are two problems which we kind of categorize as a local problem and a global problem. The local problem deals with how the reinforcement learning process actually learns. So as I mentioned, the process is roughly that we start with a completely random policy, which just takes random actions, does not know what it's doing, but it's trying to get some higher rewards. But the actual positive reward that you get, the actual kind of reward as opposed to a penalty that you get with energy optimization, is when you reach the goal and you don't have to use energy anymore. So if the agent doesn't actually know how to reach the goal, it's kind of just exploring around. The simplest way to to reduce your costs, to reduce your energy usage, is not moving anymore. So the agents will, generally speaking, learn to just stand still, because that's the way to minimize the energy cost and to minimize the penalty, and therefore to maximize the reward. But okay, let's say we fix that. We still have to deal with the global problem, which is also a property of the reinforcement learning process. And this deals with discounting, because in reinforcement learning, we typically use the discount factor as a hyperparameter for the learning algorithm, which is a controversial approach in the kind of research community in reinforcement learning, but it is what it is right now. And depending on the value of the discount factor, so what the discount factor does is that it shifts the importance of rewards such that the near term, the short term rewards are more important than the long term rewards. And again, in short term, you mostly get the penalties. Long term, you get the rewards. So if depending on the values of the discount factor and like, for example, the distance from the agent's starting point to the goal, it might actually turn out that the optimal policy for the agent is to just stand still if its objective is optimizing the discounted reward. So to fix this, our proposal number one is using an explicit guiding potential with a very specific scale. So there is this term, the 2 square root of ESEW. ESEW are the coefficients that define the energy usage. And this turns out that if the coefficient with this potential is exactly that, then the discount factor doesn't affect the optimal velocity. This is not guaranteed in general, but through some large and painful math that I will show in a second, we can prove that if the potential is this, then no matter what the discount factor is, the optimal velocity for the agent to move is the correct optimal velocity that we want, no matter the discount factor. And this solves both the local and the global problems, because it gives us a guiding potential towards the goal, so the agents will be incentivized to move towards the goal. And you also get some short-term rewards, which will solve the global problem. And this is just a very quick jump scare. This is some of the math that was involved in proving the invariability of the optimal velocity with the discount factor. Of course, I used some symbolic math approaches to do all of this, but yeah, this is fun. And yeah, then the other angle from which we're approaching this and kind of proposing another solution is using a curriculum. So the idea is that at first the agents will learn with a maybe more artificially designed, less human-like reward that will nevertheless incentivize them to move towards the goal. And then at some point when they reliably reach the goal, we can switch the reward to just pure energy optimization. It actually turns out that if we have a curriculum like that and we remove the discounting to deal with the global problem, we can, like at the final stages of the training, we can remove the potential, we can remove everything, and we can actually, in the final stages of the training, only optimize the energy. So truly to train energy efficient agents in the kind of human-like sense. So yeah, we have a bunch of experiments. I will obviously not show all of them, but we have 5 main scenarios on which we did our experiments. There's the classic circle scenario with some noise injected. There's a corridor and there's a crossing. There's a choke scenario in which they have to cross through a very narrow choke point in the middle. And there's a car scenario which maybe in hindsight should have been called the bus scenario, because the block that's below here will be moving upwards, and they just have to figure out how to go around it. And in discussing the results, I will focus on 3 aspects. So first, what is the actual impact of the acceleration correction? Then how does the energy optimization approach compare to a simpler, more artificial reward that I call speed matching, which is from my previous work when I kind of naively designed it thinking, oh yeah, this makes sense, what could go wrong? And then we'll see the impacts, both positive and negative, of the curriculum learning approach. And I hope this will work. So acceleration, I believe the first video on the left, it has the acceleration correction, so the motion is fairly smooth. I don't know to what extent this is actually visible from distance, but it's fairly smooth compared to this, where it's the exact same premise, but there is no acceleration. There's no extra penalty for accelerations. So they just kind of wiggled around because they were not penalized for that, so why not? Then this is the same scenario, but with a more artificially designed reward, which again, I used this in my prior work. And I did not use this experiment, so I did not see the absolute absurdity of this trajectory. Because it turns out if you design the reward like this, where the penalty is proportional to how far you are from your optimal velocity, the agents really don't want to stand still. They really don't want to slow down. They want to keep moving at the same velocity, which it kind of makes sense if the agents are on the bikes, where you actually want to keep the same velocity. But that wasn't the idea, so yeah. And then let's look at what happens if we have a curriculum. So on the first video, that's supposed to be the second. Okay. So this video is trained without a curriculum, where the agents, because it turns out that if you just train on the energy optimization directly, the agents become a bit more risk averse, because if you have the acceleration correction, especially a collision and stopping, and then you have to spend energy to keep moving again, it's pretty costly, so the agents become a bit risk averse, so they're just kind of moving slowly. And on the second video, which is the first video, they move a bit more confidently. They don't really, they're not that apprehensive, because here we start training with a goal-reaching reward. They confidently learn to reach the goal, and then we fine-tune the behavior to be more human-like. On the other hand, if we have a curriculum like this, okay, this time we have the videos in the correct order. This is with a curriculum, because here, when the agents were being, let's say, pre-trained with the artificial reward, they try to go in front of the car, because, I mean, they don't really care that much. And they just try to go past it. But then when they're fine-tuned to be more human-like, it turns out, oh, that's actually not a very good idea. So there's still this kind of elements of the old behavior where they're trying to run past it. Whereas if we train without a curriculum, in this case, they're just kind of casually, okay, just wait for the obstacle to pass, and then go to the goal. And that is everything I wanted to show. So as a summary, we can use energy optimization as the reward function. We just need to use some tricks to solve the local and global problems. And generally speaking, the 2 tricks that are pretty good at solving this is using a guiding potential and or a curriculum to guide the learning process. Ultimately, it still remains a little bit tricky, and this is not like an end-all be-all solution. But we, at this point, generally don't need to use weird, arbitrarily designed rewards, which I think is an upgrade over the state of the art when I was starting my PhD and trying to figure out, okay, how do I design this reward? I had no idea. And this is a crowd of kittens generated by DALL-E 3. Thank you for your attention, and welcome any questions.